Hi guys, so the exam is 50 questions long. It's pretty much comes equally from the 4 exams, so maybe slightly fewer than the first exam and slightly fewer than the fourth exam. So more heavily towards exams 2 and 3, but uh, still pretty much evenly distributed. Um, Let me first just sort of go through and show you what to expect, because remember, as I said, that I'll take these questions. In fact, I went through these questions and I just picked out 50 of them, and then I went through each question and I changed it in particular ways. So let me show you what I mean by that. Um, so for example, this first question: a mid-sized car has an approximate volume. In this car, on this question, you had to be able to estimate the dimensions of a car and then be able to calculate the area. So I could, and I did actually take this question and I just changed it by giving you something else, right? Like, what is the volume of, I don't know, this podium or whatever in cubic meters, or what is the area of your desktop in square meters or square centimeters, something along those lines. So you'll have something like that, but you'll need to know what is a meter, what is a centimeter, that sort of thing. Okay, so that's your first question, right? An estimation question where you have to estimate the volume or the area of something. Um, I could give you, in fact, I did give you some of these, yeah, a couple of these different variations, number 3 here and number 4, where are they dimensionally correct, but I just changed the equations. So you still have to do the same thing, but you just have different equations. In fact, every question, I think there are only 2 or 3 questions that I didn't change at all, that I just left them the way they were, because, I don't know, just got lazy or whatever. But practically every question has been changed. Sometimes it's sort of a subtle change, and if it is a really subtle change, I try to highlight that, because I know that y'all been studying these exams, or you will have been studying these exams, and you probably know them down pretty cold. So just a small change might escape your attention. So anyway, if it's a small change, I've tried to highlight it and bold it and all that so that it stands out to you. But just be aware that almost every question has been changed. Only a couple have not been changed. So make sure that you're aware of that and that you're not just going through saying, oh, I know the answer to this question, because likely something's different about it that makes the answer different. So you can see changes like that. Sig figs, just, different numbers. Uh, Standard for measurement, this question's on there. But not just the meter. I could ask you, what is the standard of measurement for the whatever, or the kilogram, or the second. Okay, so you can change them in ways like that that sort of expand the scope of the question. Let's see, trig, unit conversion, just different numbers. Uh, you have problems like this one right here, different numbers, or for example, like with this one, you throw something up with an initial speed of 30 meters per second. How long does it take? So what could I do to that? I could ask you the velocity at particular points along the trajectory. It would still be the same question and a similar way of approaching it, but a different question too. All right. Um, is that clear on what I mean by how I'll change the questions? Not always that simple. Usually that's it, but not always that simple. Let's see. Well, like for example, let's see. No, projectile motion is a good one. Let me show you. Good exam too. So for example, like with projectile motion, here I asked you for the maximum height. This was just a basic projectile motion problem. I could also ask for the range, or I could ask you for the velocity at a particular point. So a similar question, but I'm asking you for different things. Okay? Or I might just ask you for the same thing, but just give you different numbers. The way I'd study is to study through the old exams. I would, the solutions are online, but I would use those exams first off without any solutions at all and just work through them cold without even looking at the solutions at all. And then grade yourself and see how you did on those exams. And those that you've missed, that I'll go back and focus on those especially. Because a lot of them, hopefully, you'll just get right without even reviewing them at all. And you say, oh, I know this like the back of my hand, and you don't need to look at that anymore. Okay? Just go through and look at those that you miss, or if you get it right, if you just sort of feel a little uncertain about it, then highlight that or do whatever you need to do and go back and review those. previous test before that, then you can look for questions that are similar to the question that you're having trouble with and just give yourself a little more practice, or go back in the notes, or go back in the homework, or go back in some of the examples that we did in class. All right. Uh, I'll go through each of the exams. I'm not going to work through all of them, but we'll just sort of scroll through them. And if y'all have questions about particular things or things that are bothering you. So in exam 1, it was chapters 1 and 2, I think, which was dimensional analysis, sig figs, uh, standards of measurement, and then we also have basic kinematics, analyzing graphs. You'll certainly see all of that stuff on there in one way or another. Any of these particular topics that you have trouble with? You'll see some trig as well, but I think we got that down. Unit conversion. Students often have trouble with these, but you'll see, you know, one like 17 or 18 for sure. You'll see some analysis of graphs. You'll see stuff like this where you have to look at a graph and analyze it quantitatively. Qualitative analysis of graphs like number 21. You also see vectors, both numerical analysis of vectors, adding up vectors, that sort of thing, as well as graphical vectors. You know, there are only 100 questions, so from all semester, so basically half the questions are coming through. So you're basically seeing every topic. What on this test is particularly troublesome to you? The estimation? Okay, well with the estimation, this is hard for students. I don't understand. Uh, but it is hard for a lot of students how to do estimation. So with estimation, you really, mass is out. We didn't see any estimation of mass in the test. So we're really just looking at length, area, or volume. And so when you look at something, you need to know what a centimeter is and what a meter is. A centimeter is about the width of your pinky. All right, so like for example, if I asked you the length of this pen, you could take your pinky and say, well, 1, 2, 3, it's about 10 centimeters long, okay? Just a rough estimate. And so if I say it's about 10 centimeters long, then the options that I would give you would be 1 centimeter. Well, this thing's definitely not 1 centimeter long. 10 centimeters, 100 centimeters. It's definitely not 100 centimeters. That would be like a whole meter long, or 1,000 centimeters. And so it's going to be an order of magnitude answer by a factor of 10, and you need to pick out what is the right answer. If you know what a centimeter and a meter is, then it should stand out to you. All right? Right. Yeah, well, a meter's a yard, basically. People are about 2 meters tall. This is about a meter. The squares on the floor are about 1 by 1 meter square. A meter's about 3 feet. It's 3¼ feet. So just remember that a meter is roughly a yard, a little bit bigger than a yard. And a centimeter is about, you know, a third of an inch or so, about the width of your pinky. Okay? What's even a little more difficult is doing the area and the volume. And this question was a volume question. Yeah, so like for example, let's say that we are going to find the area of this desktop right here. Well, it's a little trickier, right? It's about a half a meter in this direction and about a half a meter in this direction. Because remember, a meter is about this long, so this is a little more than half a meter. A meter is about 3 feet, and this is maybe a foot and a half. So if it's a half a meter by a half a meter, then that would be a quarter meter. And so you might see answers like 2 square meters, or 0.2 square meters. That would be the right answer, a quarter square meter, or 2 square meters. This thing definitely isn't 2 square meters, because then it would have to be like 2 meters by 1 meter, and it's definitely not 2 square meters. All right. And similar with volume, I was telling you right up, it's not a volume problem, it's an area problem, is your estimation. But you need to know what is the centimeter and what is the meter. Okay? Is that clear? All right. How y'all on these analysis of graphs? I think that most people are okay on the quantitative. Maybe not everybody, but I think that a lot of students have trouble with things like this, like number 21, number 18, number 17. Is that still true for y'all? It's true for a lot of number 18. Yeah, let's go through it because a lot of students do have trouble with this. Um, So number 18, you have this x versus t graph, and you have to determine what is the v versus t that represents the same thing. So if you have this question, and you will have a qualitative question. There were several to pick from. I'm not sure which one I picked. But you will have a qualitative graph question like this. When you get this, you want to, in this particular case, when you see this, it'll be a similar question, but I'll just change the graph. All right. So for example, here I have this x versus t. Remember, the slope of a position versus time graph gives us the velocity. And so I want to look at how the slope changes. So here, my slope is small and negative. Right, that's a negative slope, and it's a shallow slope. And here, I have a big slope that's negative. So I'm going to be looking at my v versus t graphs that are going to start with a small negative number and end with a big negative number. So which one starts with a small negative number? It's going to be this one. Starts with a small negative number and gets more negative. That's the way you want to look at these graphs, especially when you're going from x versus t to v versus t. And largely that's what we're doing, going from x versus t to v versus t. Students have a lot of trouble with these. Let's see, you have this one too, just being able to describe it in words. Here we're looking at how the speed or the velocity, what is the speed doing? That is, it slowing down or speeding up? What's this one doing? This one's speeding up because the slope is getting bigger. Small slope, big slope. Big positive or negative slope? Negative slope. So it is a increasing speed but negative velocity. An increasing negative velocity. Increasing in the negative direction. So remember, slope of x versus t, if I have an x versus t, the slope gives the velocity, or the speed, or the velocity rather. If I have a v versus t graph, did we do v versus t? We did. A v versus t graph, we'll look at one in just a second. A v versus t graph, the slope gives the acceleration, and then also the area gives the distance traveled. We had a question on here, I think. Let's take a look. Let's see, this was a position versus time graph. I was looking for the velocity at 8.5 seconds. It's right here. So I find the slope of this line in order to find the velocity, because the slope of a position versus time graph is the velocity. You will have to find the slope. You'll have a graph. There were a couple on this test, although you could see a different graph, or I could just give you the same graph but ask you the slope at a different time. So here to find this slope, our rise is 15. Notice it's not 3, it's 15. I look at the axis over here and look at the change, and then my run is 1. Rise over run is 15 over 1. So my velocity at that point was, well, it was 16. It wasn't quite 15. It was actually a little more than that. Okay, here's a velocity versus time graph. This asks for the distance traveled. Remember, on a velocity versus time graph, the area gives the distance traveled. So here, the velocity versus time graph between 0 and 4. I just had to find this area under the graph to find the distance that it travels. In this case, each square corresponded to 1 meter traveled, because I have 1 meter times 1 meter, or 1 meter per second on the y-axis times 1 second. So each square is 1 meter, and so you just count up the squares. But that might not be the case for you, so make sure that you look at the axes and that you're figuring out what is each square. So for example, if this went from 2 to 4, then each square would count 2 meters. We had some like that in the homework and some of the older tests. So if this is troubling for you, I would go back and look at some of those. Yeah, that's fine. Position versus time graph where the velocity is slowing down. Yeah, so a position versus time graph where the velocity is slowing down will look like that. So this is a slowing positive velocity. Or I can also have it like this. This is also a slowing down, but it's a negative velocity. And again, I'm looking at the slope. Here I have a big slope, and here I have a small slope. Here I have a big slope, and here I have a small slope. It goes from being big to small. Those are the only two examples where you can have that, where it's slowing down either the positive or the negative direction. You'll definitely need to know that for Monday. Let me clear this, Joe. Let's see. Those are sort of the big things. People are generally okay on vectors, but any questions about the vectors? I've done them a lot. You'll see both graphical and numerical analysis of vectors. All right, let's go on to the next one. We can come back to this if you need to revisit it, okay? Let's go on to exam 2. Exams 2 and 3 are probably more difficult questions, the more difficult exams. You're going to see projectile motion. Make sure that you can calculate all the things about projectile motion. You really only see the two basic versions of projectile motion because that's all that you saw in this exam. That is where you have an object that starts here and goes here, or you have an object like we did in lab that goes like that. Make sure that you can calculate for those the maximum height, the maximum range, so the maximum height y, the maximum range x, or here x. Also the total time that it's in flight. Make sure that you can calculate that. The velocity at a particular time when it's in flight. You should be able to work these problems, and we had some of these in the homework very easily. You can see either one or both of those. And that's like problems number 2 and 3. But further, you also need to know just sort of basic stuff about projectile motion. Like, for example, with number 4 here, the things that are applied in projectile motion that take place in projectile motion. So things like the acceleration in the x direction is 0. The acceleration in the y direction is always -10. All the way throughout the trajectory, the acceleration in the y direction is -10. You need to remember things like the velocity in the y direction. It initially decreases, and then it increases in the negative direction. The velocity in the y direction at the top is 0. You know all those sort of basic facts about projectile motion. So like, for example, with number 4 here, I'm pretty sure this question is on the test. I could give you this question, but just change the list of facts. So it's still asking about projectile motion, but different ideas about it. So make sure you might want to go back and just revisit those things with projectile motion, the basic ideas behind it. You want me to work this problem, like for example number 2? Yeah, let's go and work that. A lot of students have trouble with it, so y'all probably do too. I always like to draw a picture. I have this projectile, and it follows a path like that. And I want to know what is the maximum height, y. In order to find that, I need to find the time, because the time's not given here, and likely on your exam you won't have the time either. So you need to find the time. The way in this case I find the time is that I say the velocity at the top in the y direction is equal to 0. And at the top, this is equal to v naught y plus ay times t. I'm going to call this t top so we can tell it differently. So I have 0 equals v naught y times 8 plus ay top. 0, v naught y is 100 times sine of 60 minus 10 times t top. All right, and then I solve that for t top. So that is 86 minus 10 t top. So that's 86 divided by 10, so t top equals, we'll just call it 9 seconds. All right? And then I solve next for y. I'll do it up here. I say y then at this time of 9 seconds is v naught y times t top plus 1/2 ay t top squared. That's going to be v naught y, which we've already found is 86. That's this 100 sine 60 times 9 plus 1/2 of ay is -5 times 9 squared. And then I can find what is my height. 774 minus, looks like it's going to be 400. Yeah, it's 400. The sig figs were a little bit off here. I got like 370, but rounding up to 400. Okay? Make sure that you can do those. You'll definitely see at least one. I think you actually have a couple of those projectile motion problems. And not just projectile calculations, but also basic ideas about projectile motion. You'll see all of that. Jacob? AY is always the acceleration due to gravity. For projectile motion problems, AY is always -10 meters per second squared. Now remember, this is a little bit different when we get into chapter 4, when we're calculating the weight. That's mg. The g has a positive value for the reasons we talked about. Okay? So make sure you're up on projectile motion. I said a lot of students have trouble with it, so it's something that you'll see. Lots of questions on this exam about projectile motion. Like there's probably 5, 6 different questions here about projectile motion. You'll see several of those on the exam. Absolutely. Okay, here at point y, what is the direction of the velocity? When you revisit the projectile motion, you'll see we had this figure that we did in class where we talked about how the velocity changes. We have Vy that is in that direction. It goes down, it goes to 0, and then it increases in the negative direction like that. And then Vx is always the same. It doesn't change because Ax is equal to 0. So this is Vx. So a similar thing here. We're just looking now at the second half of that motion, starting at the top and going down. And so at part y, we have vectors that look like this. What it's asking for is the direction of the velocity, the net velocity, not the x or the y alone, but the net velocity. And if I add these two vectors up, I get a vector that's in that direction. And so that was B for the right answer. I don't know if you see that question particularly. I don't remember, honestly. But you do need to know sort of how the velocity vectors change throughout the trajectory. Okay, is that clear? All right. Anything else about projectile motion? We can come back to it if y'all want. Newton's laws, you're going to see an inclined plane. You're going to see a couple of problems with friction. You're going to see a 2D force problem as well as a 1D force problem. So you see lots of different examples here. Like, for example, number 14 here. Number 16, that's a 1D force problem. I pulled a lot of these problems and changed them up a bit. So of any set of problems, the Newton's laws problems probably have the most representation on the exam. So it's pretty much equal among all the 4 exams and all the different topics, but this probably has the most. Number 16, yeah, number 16, you're going to have an inclined plane with or without friction. So like, for example, with this one, I'm not saying that you will have an inclined plane. It is very similar to this one, but I could change it in a variety of ways that make it a little more difficult. I can make it where it's not at a constant speed, but it's accelerating. Could also add friction to it. That's really all I could do. Okay? You can work the inclined plane problem, okay? Just one nod and I'll work it out. Yes? You want to work this one out? I think it'd be worthwhile. Let's do it. All right, so I have this 5 kilogram mass. It's being pulled up at a constant speed. When it says constant speed, that means the acceleration equals 0. And that affects how we work it, or how we solve Newton's second law. The first thing you want to do is just draw the forces. So I have the tension here, Ft. I have my normal force, Fn. And then I have my weight. And my weight goes down like this, but then I can break my weight into its x and its y components. I have FW sine of 40, and I have FW cosine of 40. I'm not going to get into the geometry of why this is. We did this in class, but remember, if you need to go back and look this over, if you have questions about it, you can ask me later. But when I do these components, the angle is 90 minus this angle. And then I do the cosine of 90 minus that angle. And that's why this is 40, whereas this angle is 50. Okay? It's the way we draw our coordinate system, why it comes out like that. Hopefully you can get to the point where instead of drawing this weight vector, you just draw the components of the vector, and that'll help you a lot. And then this one was fairly simple, because if it has an acceleration of 0, that means the sum of the forces in the x direction equals ma, which is equal to 0 because the acceleration is equal to 0. If that acceleration was not equal to 0, then it would equal to m times whatever the acceleration is. And the sum of the forces in the x direction is going to be ft minus fw cosine 40, and that's equal to 0. And then you solve for ft, which is fw cosine of 40. That was 50 newtons. It was a 5 kilogram mass, and so I multiply it times 10, m times g, to get the weight of 50 newtons times the cosine of 40, which is 38. And so that is the tension, 38 newtons. Again, a couple different ways I could change this. I could add a frictional force, Fk. The frictional force, if I added a frictional force, you'd have to figure out what is the normal force. And so you'd say the normal force is 50 sine of 40. That's 32 newtons. And then Fk would be mu k times that normal force. Let's say that mu k was 0.1. The normal force is 32. That's 3.2 newtons. And so then I would have this extra force in my sum of the forces up here. That would be Fk. And that would change what is the tension. It would make it a little bigger. It would actually make it, I would have a plus Fk plus 3.2, and then this would be 41 newtons instead of 38 newtons. So that's one way we could change it. Another way we could change it is not make A equal 0, but make A equal, I don't know, say 1 meter per second squared. And here, when we draw some of the forces in the x direction, Ft minus Fw cosine 40, instead of setting that equal to 0, we'd set it equal to 5 kilograms times 1 meter per second squared. So those are a couple of variations. You could add friction, and you could add an acceleration. Make sure that you're okay with both of those. They come up in several different problems, so you could see those elsewhere as well. Okay? Need to be up on both of those. Your friction and your accelerating, your non-static, or where your sum of the forces is not 0, where it is accelerating. Can I clear this, y'all? Is this overwhelming? Or is sort of like, okay, or hopefully it's showing you places where you need to go back and review things. Okay, you're going to have a problem like this. It looks very similar to this. I give you a set of equations. They're different from these, but make sure that you can do it. Where you have to write out the equations, or you have to pick out which equations are incorrect. All right? I think you see one like this. I'm not positive. Okay. Just a hint for you. Hopefully you know this, but you know the exams are laid out chapter by chapter, and it'll be the same for the final. So chapter 1 questions come first, chapter 2 questions come next, 3, 4, and on and on. So you should be able to tell when you get into a section that, okay, I'm dealing with Newton's laws, okay, I'm dealing with work, now I'm dealing with momentum. And you can use your equation sheet too. You'll have the equation sheet that's on the website to sort of help you remember the order of those chapters. But remember, The equations for chapters 1, 2, 3, and 4 are not on there. But there aren't that many equations. They're really just the two kinematics equations, F equals ma, and the trig functions and stuff. Okay? That's why we don't have those chapters on there. Let's see, anything else here for chapter 4? The inclined plane, friction, forces. Make sure that you're up on your various conceptual questions that we had about the laws, Newton's laws. Yeah, gonna go on the next topic. This is a big topic though, so make sure that you're up on it. Let's see, what else we have here? Oh, work. We didn't have much on work on this test, but you will see it. Uh, you could see units. You could see units for any of this stuff. Um, Positive, negative work, you'll likely see that here, where if the force is in the same direction of the displacement, that's a positive work. If it's opposite direction of the displacement, or a component of the force is opposite the direction of the displacement, that's a negative work. Being able to calculate the work, that's on your equation sheet, but our work is FD cosine theta. Like that. Perpendicular is 0, right. The reason is that the angle between F and D is 90 degrees, and the cosine of 90 is 0. Students tend to get work a little bit better than the other things. But would you like me to work in any of these? It comes up again in the next test too. So let's go on to exam 3. Let's look at this one, because you're going to see it, and I think it's just the math is a little tricky, so I'm going to show you. All right. Takes 100 meters to stop a car initially moving at 25 meters per second. The distance required to stop the same car at 50 meters per second under the same conditions is what? So what we're doing here is force times displacement is equal to 1/2 mv squared. This is our work energy theorem, that if I do work on an object, it changes its energy. Okay, so I have this force that I don't know what the force is, like it's like a truck going into one of those sand pits or whatever, right? The sand exerts a force on the truck and causes it to slow down. But it takes 100 meters to stop this car that's moving at 25 meters per second. So this force times 100 meters is 1/2 m 25 meters per second squared. Uh, what happens if I double the speed? What happens to the distance? Well, if I double this 25 meters per second, make it 50 meters per second, since it's squared, I get a factor of 4 over here. V is squared. If I double V, that means I get a factor of 4 on the right-hand side. I have to have a factor of 4 on the left-hand side as well. So where it was 100 meters, now it's going to be 400 meters. Okay, but let's say instead of that, what if I would do it the other way around? Let's say that instead of, I tell you that it now takes, say, 25 meters to stop. So that's 1/4 of 100 meters. So it takes 25 meters to stop. What, you follow what I'm saying? What is the velocity that the truck was moving at if instead of taking 100 meters, it takes only 25 meters? So I have a quarter over here. I need to have a quarter over here by changing my velocity. By what factor does my velocity change? Not 16. What squared gives me a quarter? what times itself gives me a quarter? What times what equals 1 over 4? What is it? Well, 1/2, right. So 1/2 is the answer there. Because 1/2 squared is equal to 1 over 4. Okay? People really have trouble with those types of questions, but you will have one that's similar to this. It's a little bit different, but it's very similar to this, okay? All right. You're going to have conservation of energy, like this problem. It'll be, I might have even used the same figure, I don't remember, but I could ask you at any one of these points, change the speed or the height or whatever. Just make sure that you can find the velocity or the height at any one of these points. You okay with this? You work through this? Okay for now. We can come back to it if you want. So, um, and then also, how does the kinetic energy change? Talk about what is the potential in the kinetic energy. So, for example, here, my potential and my kinetic, it has both potential and kinetic. Down here, it only has kinetic. Up here, it has both potential and kinetic. And up here, when it comes to stop, it only has potential energy. The potential energy is 0 when the height is 0, like here. My kinetic energy is 0 when the velocity or the speed is 0. Make sure that you're aware of that and are able to answer these questions like number 4. Number 5 is another one of those relationship problems. If I double my velocity, in order to keep this equation consistent, I have to quadruple my kinetic energy. Conservative forces, and you know about that. Elastic potential energy as well. This is a similar question. I'm setting my kinetic energy equal to my elastic potential energy. You have the equations for those things on your equation sheet, but you need to be able to apply them. It's conservation of energy. It's a lot like the roller coaster problem, but with elastic potential energy. That's right. So kinetic energy is 1/2 mv squared. If I increase this by a factor of 3, I get a factor of 9 over here. If I increase it by a factor of 1/2, I get a factor of 1/4 over here. Half squared is 1/4. All right? If I increase it by a factor of 1 over square root of 2, what do I get over here? 1/2, right? Because square root of 2 squared is 2. Right? Square root of 2 squared is 2. Root 2 times root 2 is 2. Good question. Students have a lot of trouble with that. So if you're having trouble with it, that's okay. You're with a lot of good students that also have trouble with it. Okay, let's see. These are all spring problems. I don't think you had a Hooke's law. There is no Hooke's law. This question is not on there, but there are conservation momentum problems. This is the machine gun problem. People didn't do very well on it on the test. I didn't put it on the final. But there is a collision problem where you have to solve for either the final or the initial velocity. So you have this before the collision and after the collision. You have to find one of the velocities, either initial or final. Okay. In order to do that, you say that the initial momentum is equal to the final momentum. In this case, being careful with your signs. So here we had mass times velocity, 2 times positive 4, plus 4 times negative 3 equals to, in this case, this was a perfectly inelastic collision. That just means they stick together. So my mass is 6 kilograms times V final, and you solve that for V final. They don't have to stick together. If they don't stick together, then you have to have one of the velocities of the after the collision, the post-collision. But you will have one like that. Need to be up on these various conceptual problems. I think you have a impulse problem that is F is equal to delta P over delta T. If you know the change in momentum and the time in which it occurred, then you can find the force that acted to change that object's momentum. It's very hard to measure forces, but it's very easy to measure speeds, and so it makes a nice way to measure a force without actually measuring the force. The problem that students have often is with the signs. So here I have my initial and my final speed. And a lot of students would look at that 4.5 and 4.2 and say the difference in those is 4.3, or is point 0.3 rather, but that's not the case because you have to look at the signs. My change in momentum is equal to my mass times my change in velocity. That's m times vf minus vi. So this was 0.3 times vf is 4.2 minus vi, which is negative 4.5. So people often forget this sign right here, which causes you to add up the numbers. And my advice to you is when you see one of these problems, instead of trying to take the difference, you just add the numbers up. You're always going to add them up. So 4.2 and 4.5, you'd say, when I take the difference in those, it's going to be 8.7 instead of 0.3. Okay? That's often a mistake that students make. But of course, that mistake is reflected in one of these answers. So if you make that mistake, you might not recognize it right off. Okay, so that's, and then you divide that by the change in time, which in this case was 0.03 to get the force. I forget what it was. Erase this. Is this useful for y'all? Because y'all look really excited about it. Okay, other stuff about momentum here. Make sure that you're up on all these, that you sort of know the relationship between mass, speed, and momentum. Like for example, and also like number 15, 16. I'll let y'all do these on your own. But any questions about these, actually? You to address any one of them in particular? All right. Now we're into chapter 7. You need to know your revolutions, radians, and degrees, how to convert between them. We had a couple different questions, 20 and 21 here, about those. The centripetal acceleration. Remember, centripetal acceleration is v squared over r, where v is our speed. But also don't forget that if I don't have v, I can also do omega squared r. This is just substituting in v equals omega r. All these equations are on your sheet. This isn't on there, I don't think, but these two are on there, so you can substitute them in to get them. Here you had one about centripetal force. Remember, centripetal force is mv squared over r. For this problem, you just had to recognize that the centripetal force is the tension. And so really here, I'm just asking you to find the centripetal force. So the tension is 80. And so you say, well, that 80 is my centripetal force. And then you're solving for the speed. You'll have a kinematics problem. It'll be similar to this one, but different, where you're using those kinematics equations. Remember, it was theta equals omega naught t plus 1/2 alpha t squared, and omega equals omega naught plus alpha t. Looks like for this one, you're using the first one, but I could change the problem where instead you're looking for velocity. These equations are on your equation sheet. And by the way, if you forget the equations for chapter 2, you can look at these and remember, well, theta is x, omega is v, and alpha is a. And then you revert back to those linear equations, and they're the same. All right, that's exam 3. And exam 4 is probably pretty fresh in your mind. Anything particular on exam 4? Again, I could change things, change numbers. For example, number 1, I could ask, well, no, that's not a very good one. Number 4, I could change the shape. In fact, you will see that where I changed the shape. Number 5, I could change, this is a bar, I could change it to a sphere or disc or whatever. You'll see a torques problem. You'll see a problem where you have to apply Newton's second law. That's that sum of the torques is I alpha. You can see torques here where you're ranking them. You have a couple of ranking problems. I forget what they were about, but you do have a couple of those. Let me zoom in a little bit so you can see better. Yeah. That's right. So you have a couple of cases where your torque can go to 0. You can have your torque be 0 if it's acting at the axis of rotation. Because remember, torque is Fr sine theta. And so if R is equal to 0, your torque is equal to 0. The other way is if theta is equal to 0, like for example with this force, then your torque is 0 because the sine of 0 degrees is 0. So if you're acting at the axis of rotation, or if your angle is 0 degrees, then it's going to provide no torque. And if you think about this, right, if I have an object that's rotating about this axis, this force does nothing to rotate it. It's just going to pull on it and not make it rotate at all. But you will have one like that where you have to find the net torque and then apply Newton's second law in order to find its acceleration and then maybe its velocity or how far it goes, how many revolutions or radians rather it rotates through, something like that. And then we move into chapter 9. You have a few questions about this. You do have an Archimedes problem. It might not be exactly like, excuse me, number 11. Sorry. It might not be exactly like number 11, but something similar to this. Number 11, sure. Here you have a boat. It's a rectangular prism. You have the area dimensions, but the volume of this boat is going to be 2 times 1 times the depth, d. And you're looking for the depth. You also need to recognize that it's floating. This boat is floating. And because it's floating, the buoyant force is going to equal to the weight. Right? Because if I have this boat, the buoyant force has to equal the weight. Otherwise, if it's less than the weight, it's going to sink. Okay, so the buoyant force is equal to the weight, and the weight here is 5,000 newtons, 500 times 10. I also know that my buoyant force is the density times the volume times g. That's the density of the fluid, which is water, the volume of the object times g. So what you had to do here is you had to say that the buoyant force, which is 5,000 newtons, I know that because it's equal to the weight, is equal to the density of water, that's 1,000. That's on your equation sheet, but I recommend that you just know it. It's a good number to know. Times the volume of the object, I don't know that right off, times g, which is 10. That's 5,000 over 10,000. So the volume of the object is 0.5 cubic meters. But I can go back up here and say, well, this has to equal to 0.5 cubic meters, and I solve for this unknown, which is d. D has to be a quarter, 1/4, or 0.25 meters. So you can see something similar to that. Yeah, something similar to that. You will see Archimedes' principle in a couple of problems. Okay. Um, need to know all these principles. Like, for example, number 14 asks about Bernoulli's principle, but I could change it simply. I could say, well, what does Pascal's principle say? Or what does Archimedes' principle say? So, for example, here, this one is Pascal. This one is Archimedes. Uh, this one is Bernoulli's. And this one is the equation of continuity. So we have all of those rules that we studied in this chapter that are all the different options. C here is actually an incorrect way of saying Pascal's principle. It's sort of Pascal's. A small input force always causes a large output force. That's like what we saw in problem 17, but that's not necessarily always true. So that would not be Pascal's principle. It's sometimes true for Pascal's principle, but not necessarily always true. Okay? Can I clear this? Sure. Okay, a swift wind blows across the top of a chimney. What happens to the smoke rising inside of the chimney? So if you have this chimney, and you have smoke that's rising up, and you have this fast wind that's going across the top of it, This comes back to Bernoulli's principle. Bernoulli's principle said, oh, where was it? Well, Bernoulli's principle says that if the pressure, or excuse me, if the speed goes up, the pressure goes down. In an ideal gas, if the speed goes up, the pressure goes down. So up here where I have a high velocity gas traveling, that means I have a low pressure. So if I have a low pressure, I get this net force that's pushing, I get a high pressure down here, a low pressure at the top. That forces the smoke up the chimney. Right? But it's an application of Bernoulli's principle, that if I have a high velocity, that means I have a low pressure. High velocity is low pressure. It comes about from Bernoulli's equation, which said that P plus 1/2 rho v squared, that this has to be a constant value. Remember, it comes about from the conservation of energy, that the energy per unit volume is always the same in an ideal fluid. Remember, there was a third term, and this is on your equation sheet, but we're not going to worry about it because our height doesn't change in our examples. So if V increases, that means P decreases, assuming the density remains constant, which it does for our ideal fluids. Okay? Alrighty. Pressure measurements, make sure you can do that. Remember, make sure that you're aware that P is P naught plus or minus rho GH. Make sure you can tell the difference whether it's plus or minus. Here it was minus, but it could be different. Number 21 was Young's modulus. These really, the hard part is just knowing what the values are. So you had to pick out that, well, let's see, this is my A, this is my L, my original L, this is my force, and then you had to find the Young's modulus for bone on your equation sheet. So just make sure that you're able to use those equations properly. Not a whole lot from chapter 10. Um, need to know your temperature measurements. There wasn't a whole lot on this test from chapter 10, so you won't see a whole lot on the final. But you do need to know, ideal gas law, how to apply the ideal gas law, uh, the temperature scales, sort of how to convert temperatures like 27 here, how to measure temperatures, linear expansion like 24. I would just sort of go back and, work through these. They won't be terribly different from these. That's the good news about this chapter 9 and 10 is that, you know, the problems can't be changed up that much. So if you're able to do them, you're probably okay. All right, there's a lot on this test. It's chapters 1 through 10, so a lot of different topics. Fortunately, some of them build on one another, so they sort of run together, but there's still a lot on the test. And almost every topic is covered. There's very little that's been left off. Right, Joe? How y'all feel about it? I don't know right off, but I try to have more conceptual than because students tend to be able to do those more quickly. Do you have a question, Tricia? Yeah. Number 7? Okay. Yeah, you'll have one like this for sure. Uh-huh. How do you find the net torque? Okay, in this case, you first need to figure out which is positive and which is negative. So this force right here causes a what? Counterclockwise torque. So it's a positive torque. That one's counterclockwise. And this one causes a clockwise torque because if I pull down in this direction, it causes this thing to go in this direction, which is clockwise. So this is a negative torque. And so I'm going to have 30 newtons times 1 meter minus 10 newtons times 1 meter. The angle here is 90 degrees, so I just leave off that sine theta, because sine of 90 is 1. So that's 30 minus 10, or 20 newton meters. comes out positive, so that means it's going to be counterclockwise. All right. Does that answer your question? Okay, awesome. But yeah, students have trouble with that, figuring out if it's clockwise or counterclockwise. I recommend to you that you just sort of forget about the other force and sort of try to imagine the object. If I pull down on this direction, it's going to make it rotate in that direction. That's clockwise. Over here, this force, if I pull in this direction, makes it go counterclockwise. Okay? But you'll definitely see something like that. All right, number 9. Any other questions, Joe? Okay, we have the weekend and a day, so let me know if I'll be around tomorrow if you have more questions, you can just drop by my office. I don't think I have anything going on tomorrow, so I'll be in my office practically all day. All right? Okay. Yeah, exam 3, you know what? I had to change the order around. It didn't affect your grade. Like I used the right key. If you really want the electronic copy of your actual exam, shoot me an email and I'll email it to you. Yeah, I'm sorry. It's just at the last minute before I printed the exam, I had changed the order around so that I could fit it on the right number of pages.